Hello everyone, this is lecture 9. So in the lecture 9, I'm going to break the lecture into two different parts. The first part is about finding the equation of a line in three-dimensional space. And in part 2, where we focus on finding the equation of planes in three-dimensional space. So in pre-calculus and calculus 1, we focus on finding linear equations in two variables, that is y equal to mx plus b, given a slope, given a point, given a y-intercept, and the lines lied in the xy plane or two-dimensional plane. So the aim of this lecture, or the first part of lecture 9, is to begin a similar journey through three-dimensional space. That is, what are the basic geometrical objects in three dimensions and how do we describe them with equations? And certainly among the most fundamental objects in three dimensions are lines and planes. So similar to the 2D plane, in 3D space, two distinct points will allow us to determine a unique line. In addition to that, if you have one point and the directions of the line, we could be able to determine a unique line as well. We're going to use both of these properties to derive different descriptions of lines in space, including lines in vector forms, parametric form, and symmetric forms. And also at the end, we're going to learn how to describe the relationship between lines. We want to know if the lines are equal, parallel but not equal, intersecting, or skew. So that's the main objective of this lecture. So again, equations for a line in space, we can definitely describe a line in space using 2 points and a point and the directions of the line. And the directions of the line, I'm going to use different terminology interchangeably throughout the lecture. So the direction of the line, I can also say the parallel vector or directions vector. I'm going to give you some definitions to see if the two vectors are parallel or not. So I have two non-zero vectors, u and v. These two vectors are parallel if and only if vector u is equal to k times vector v, where k is a scalar, or just a constant for that matter. So it means that vector u is a multiple of vector v. And we have learned about this earlier when we talk about two-dimensional or three-dimensional vectors. That is, depends on the value of k, u and v may point in the same directions or they will point in the opposite directions. It doesn't matter which direction they point, as long as u is equal to k times v, u and v are parallel to one another. But certainly when k is positive, u and v points have the same directions. When k is less than 0, u and v have the opposite directions. And by convention, we have that the zero vector is considered to be parallel to all vectors. So by convention, the zero vector is considered to be parallel to all vectors. Okay, so that is definitions for parallel vectors. Again, the two vectors are parallel to one another if one vector is written in terms of a multiple of the other vectors. I want to give you another definition, that is the positive vector. If P is any point and O is the origin, then the position vector of P relative to O is the vector OP. Then the position vector of P relative to O, or to the origins, is the vector OP. So you have seen this position vector before, so consider the three-dimensional space of x, y, and z. And the vector OP, or the position vector, can be described using this particular vector. So here, this is vector OP, given that O is the initial point and P is the terminal points. And sometimes this type of position vector can be denoted as vector R. So in this case, vector R is a position vector. Okay, so with these two definitions, I'm going to move on to finding the equation of the line in three-dimensional space. When you look at this image, you have three-dimensional space, x, y, and z. There is a line L. We're going to come to that later. We have three different positions vector, R0, R, and V. And you need to notice that the line L is parallel to the vector V. Now on the line, there are 2 points. The first point is P, and the second point is Q. Here I denote that P is equal to x0, y0, and z0. And Q is going to be x, y, and z. And these 2 points again are on the line of L. And if you form a vector from P to Q, that is P is the initial point and Q is the terminal point, I have a vector PQ, or I have the vector A. And as mentioned before, the line L is parallel to the position vector V. And therefore, since L is parallel to v, which is an assumption that we have to make. V is the directions vector of L. So what is the direction vector? If you go back to the beginning here, you have the direction vector is also considered to be parallel vector, and the parallel vector is given in this particular form. So again, go back to our derivations here. V is the directions vector of L. That means for some scalar t, we have that vector PQ is equal to t times vector V, right? Because the two vectors are parallel to one another. And when you form the vector PQ, you have x minus x0, y minus y0, and z minus z0, which is equal to t times A, B, C, given that V is equal to, so the position vector V is A, B, and C. So again, that's the assumptions that we have to make. So where V is equal to A, B, and C. Then what we're going to do is we're going to distribute scalar t into A, B, and C. And we're going to have x minus x0, y minus y0, comma z minus z0 equal to t times A, t times b, and t times c. Now from this equation, what we're going to do is we're going to match the component of the two vectors. So x minus x0 equal to t times a, y minus y0 equal to t times b, and z minus z0 equal to t times c. So that is, you have x minus x0 equal to t times a, y minus y0 equal to t times b, and z minus z0 equal to t times c. Then we can solve for x, y, and z. So from the first equation, you get x equal to x0 plus t times a, y equal to y0 plus t times b, and z is equal to z0 plus t times c. So these equations that we just obtained is called the parametric equations of a line, given a point and the directions vector. So this is the parametric equations of a line given a point and a direction vector. Alright, so that's one form of equations of a line. Now I'm going to write out a more formal definition for the parametric equations of a line. So that is a line L parallel to a vector positions V, A, B, and C, and passing through the point P equal to x0, y0, and z0 can be described using the formula x equal to x0 plus at, or t times a, doesn't matter, y is equal to y0 plus b times t, and z is equal to z0 plus c times t for parameter t. Now from this equation, we can actually solve for the value of t for each equation and create a new form of equation of a line, and the new form can be described as symmetric equations of a line. So from this equation, you can solve for t, and you get that t is equal to x minus x0 divided by a. For the second equation, you can solve for t as y minus y0 divided by b. And for the last equations, you have t equal to z minus z0 divided by c. And because they are the same t's, I'm going to set these equations equal to one another, and you obtain something called the symmetric equations of a line. That is x minus x0 divided by a equal to y minus y0 divided by b equal to z minus z0 divided by c, where a, b, and c are non-zero constants. In addition to parametric equations of a line and symmetric equations of a line, we have another form that allows us to write down the equation of a line, and that is vector equations of a line. Now let me go back to this image here. As you can see on the graph, you have three positions vector, R0, R, and V. We already know that vector V is parallel to vector PQ. What about R0 and R? So R0 and R, again, are positions vectors. We're going to go from this point P to the point Q, and at the position P, you can form a vector OP. Right. And if you travel a distance a, or the magnitude of a, you have a new position vector that is r, formed by connecting the origins and the point q. So therefore, the vector positions r can be formed using the connections of the original position vector and the directions vector. So let's set r equal to x, y, and z, and r0 is equal to x0, y0, and z0. To go from r0 to r, we take a distance of a, and a is parallel to v. So therefore, you have the vector equation of the line. With the direction v is r equal to r0 plus t times v, for t is a parameter. These are the three equations of a line in space. Again, what we need to find the representations of this equation is a point and directions in space. Now we're going to apply this knowledge to some example. So consider the first example. We want to find parametric equations, symmetric equations, and vector equation of the line passing through the 2 points 1, 4, -2, and -3, 5, 0. We just learned that 3 different forms to write the equation of the line. You get a point and the directions vector. We haven't talked about forming a line using 2 points. Okay, so here is the chance for us to learn that particular approach. So when you have the 2 points on the line, you can find a vector given the initial point and the terminal point, and that vector is considered to be the direction vector. So I'm going to call this point P and this point Q, and I can form a vector PQ that is -3, -1, comma 5, -4, comma 0, -2, and I'm going to get -4, 1, 2, and again this is the direction vector. So let this equal to V, and this is direction vector. Now, given a point, choose any point you like, and the directions vector, we can write down the parametric equations of the line. So the parametric equations of the line are, so you have x equal to x0 plus a times t, y equal to y0 plus b times t, and z equal to z0 plus c times t. Given a point here, I'm going to choose the point P, 1, 4, -2, and you have a directions vector of -4, 1, and 2, and that's going to be A, B, and C. And this one right here is x0, y0, and z0. So the parametric equation of the line is written as x equal to 1 minus 4t, comma y equal to 4 plus t, comma z equal to -2 plus 2t. Now to form a symmetric equations, we solve for t for each equations. So to obtain the symmetric equation, we solve for t in each equation above. So that is for the first equation, I get t equal to x minus 1 divided by -4. So just leave the -4 like that to indicate the value of the direction vector or the component of the directions vector. And then for the second equation, I get t equal to y minus 4 divided by 1. So usually we don't have to write divided by 1, but again, you want to keep the form of the direction vector. And for the last equation, I get t equal to z plus 2 divided by 2. And I'm going to set these equations equal to one another, and I get x minus 1 over -4 equal to y minus 4 over 1 equal to z plus 2 divided by 2. And again, this is a symmetric equation. Now for the last form, or for the last type of equations, vector equations, what I'm going to do is I'm going to consider the two position vector, vector r0 and the vector r. So the vector r is equal to r0 plus t times v, for r0 is the position vector from the origin to the point P. And r is the position vector from the origins to the point x, y, z, that is any point along the line. So the vector equation is written as r equal to r0 plus t times v, for r0 is equal to 1, 4, -2. Again, how I get 1, 4, -2, r0 is the positions from the origins to the point P, therefore I get the vector to be 1, 4, -2, plus t is the parameter, times v is the directions vector, which we got earlier here, -4, 1, and 2. So that's it for this example. In this example, again, we try to obtain equations of the line in 3 different forms: parametric equations, symmetric equations, and vector equation form. Now we're going to do the same thing for the next example. We also consider 2 different points, 1, -3, 2, and 5, -2a, and these 2 points are on the line that we're looking for. So the first thing we need to do is to determine the directions vector. So the directions vector, v is equal to 5 minus 1, comma -2, minus -3, comma 8 minus 2, and the directions vector is 4, 1, 6. From here, you can write down the parametric equations of the line given a point in the direction vector, and the point that I want to use here is 1, -3, 2. So the parametric equations are, you have x equal to x0, in this case is 1, plus a times t, so that is 4t. The second equation is y equal to y0, which is -3 in this case, plus b times t, for b is equal to 1 in this case, so just plus t. And z is equal to z0, which is 2 in this case, plus c times t, plus 6 times t. Now to obtain the symmetric equations, we're going to solve for t for each equation that we just got. So to obtain the symmetric equations, we solve for t S. So t is equal to x minus 1 divided by 4. In the second equation, you get t equal to y plus 3 divided by 1. And for the last equation, I get t equal to z minus 2 divided by 6. And we set these equations equal to one another, and we get, so x minus 1 divided by 4 equal to y plus 3 divided by 1 equal to z minus 2 divided by 6. So this is the symmetric equation of the line. Now for the vector equation of the line, again, I'm going to consider two position vector r0 and r. For r0 is the position vector from the origins to the point here, 1, negative 3, 2. And r is the position vector from the origins to any point on the line. So I'm going to call that point x, y, and z. So the vector equations is of the form r equal to r0 plus t times v. For r is equal to x, y, and z, and r0 is the vector 1, negative 3, 2, plus t is the parameter, and v is the directions vector of 4, 1, and 6. So these are the three types of equations of the line: parametric equation, symmetric equation, and vector equation. Now we're going to move on to the next topic, which is we're going to determine the relationship between lines. We want to classify if lines are equal to one another, parallel but not equal, intersecting one another, or skew. And we need to know whether the directions vector are parallel if the lines are sharing the points. So the direction vectors are parallel, or the lines share a point. And I have a table here that's going to help us classify the relationship between lines. For the top table, we want to know if the lines share a common point. Here, we want to know if the directions vector are parallel. If the answer to these questions are yes, then we say that the two lines are equal. They do not share a point, but the directions vector are parallel. Then you conclude that the two lines are parallel but not equal. And when they share a common point, but the direction vectors are not parallel, then you say they're intersecting. And if the answer to these two questions are no, then you say that the two lines are skew. So let's go into classify the relationship between the two lines following this information. So we want to determine if the two lines L1 and L2 are equal, parallel, not equal, intersecting, or skew. So what we want to do first for each line is to determine the directions vector. Okay, so for the first line, or line 1, the direction vector is v1 equal to, so s in this case, as you can see, is the parameter. So the number in front of the parameters will combine together to get the direction vector. So that is for the first line, the direction vector is v1 equal to 5, negative 2, 3. Now for the second line, the direction vector is v2 equal to, so this equation is written in symmetric forms, and the number in the denominator of each fraction is going to help determine the direction vector. And you can see here v2 is also equal to 5, negative 2, and 3. So the two directions vector are equal, so at least we know that they are either equal or parallel to one another. So since v1 equal to v2, L1 and L2 are either equal or parallel. So from the first line, you see that the lines is written in the parametric form, given a directions vector and a point. And the point on line 1 is 1, 2, and 3. And substitute that point in line 2 to see if we get the 0 results. If two lines are equal, they have to go through the same points. Then consider the point 1, 2, 3, and substitute this into L2. We get that 1 minus 1 divided by 5 is equal to 0. Then 2 plus 3 divided by negative 2 is equal to negative 5 over 2. And for the last one, you have 3 plus 1 divided by 3, which is 4 over 3. So this shows that 1, 2, 3 does not belong to L2. So we conclude that L1 and L2 are parallel but not equal. So this shows that point 1, 2, 3 does not belong to L2. Thus, L1 and L2 are parallel but not equal. So in example 4, we want to determine the point of intersections of the two lines L1 and L2 if one exists. So it's not very clear to us if these two lines are intersecting one another or not. So we have to show that first. First, we want to make sure that the two direction vectors are different from one another to show that the two lines are either intersecting or skew. So from L1, the direction vector V1 is going to be 1, negative 2, 4. And for L2, you have the directions to be 3, 1, negative 1. So here you conclude that V1 is different from V2, implying that L1 and L2 are either intersecting or skewing. So from line 1, I have the parametric form of the form x equal to 3 plus s, y equal to negative 7 minus 2s, and z is equal to 5 plus 4s. I'm also going to write line 2 in terms of parametric equations. So line 2 is going to be x equal to negative 7 plus 3t, y equal to negative 8 plus t, and z is equal to 4 minus t. So these two lines are written in the same form, which is the parametric equations. So now suppose L1 and L2 are intersecting, then we can obtain the following system of equations. So suppose L1 and L2 intersect, then we obtain the system of equations as follows. So I'm going to set the x equal to one another, the y value equal to one another, and the z value equal to one another, and therefore I'm going to get the system of equations. So the first equation is 3 plus s equal to negative 7 plus 3t. The second equation is negative 7 minus 2s equal to negative 8 plus t. And the last equation is 5 plus 4s equal to 4 minus t. So what is the reason behind this approach? We want to find if L1 and L2 intersect one another or are skew. We're going to solve for the value of s and the value of t. And the value of s and t in each of these equations is going to be the same, or give you a true statement. If that is the case, you say that the two lines are intersecting one another. If they give you a false statement, then you say the two lines are skew. So for the first equations, I'm going to solve for s. So that is s equal to negative 10 plus 3t. We're going to substitute s into the second equation. It doesn't matter which equation you're going to substitute next. But I'm just going to substitute s into the second equations. Then substitute s into the second equation into negative 7 minus 2s equal to negative 8 plus 7. We get that negative 7 minus 2 times negative 10 plus 3t equal to negative 8 plus t. And from here, you can solve for t. So I get negative 7 plus 20 minus 6t equal to negative 8 plus t. And if you solve the equations correctly, you should get t equal to 3. From t equal to 3, we can get the value of s. Then you have that s is equal to negative 10 plus 3 times 3, which gives you negative 1. Next, we substitute s equal to negative 1 and t equal to 3 into the third equations. And by doing that, we should get the true statement if the two lines are intersecting. And if you have the false statement, the two lines are skew. So substitute s equal to negative 1 and t equal to 3 into the third equations. 5 plus 4s equal to 4 minus t. We obtain 5 plus 4 times negative 1 equal to 4 minus 3. So on the left-hand side, you get 1. On the right-hand side, you also get 1. So this is the true statement. So this confirms that L1 and L2 are intersecting. And of course, to determine the point of intersections, so to determine the point of intersections, we substitute s equal to negative 1 into L1 or t equal to 3 into L2. We get that x is equal to 3 plus negative 1, comma y equal to negative 7 minus 2 times negative 1, and z is equal to 5 plus 4 times negative 1. And therefore, the point is 2, negative 5, and 1. So that is the procedure to determine the point of intersections between the two lines, assuming that two lines are intersecting one another. Now we're going to use the same approach for the next example. So in example 5, we want to determine the point of intersection of the lines y1 equal to x equal to 4 plus 2s, y equal to negative 5 plus 4s, and z is equal to 1 plus 3s, and line 2 equal to x equal to 2 plus t, y equal to negative 1 plus t. So can you fix that for me, please? And z is equal to 2t. Okay, and again, what we want to know is first to determine if the two lines are intersecting one another before you can find the point of intersections. So first, we want to determine the two directions vector are different. If they are different, we can conclude that the two lines are either intersecting or skew. So for L1, the directions vector V1 is equal to 2, 4, 3, and L2, you have V2 is equal to 1, 3, 2. So from here, the two lines or the two directions vector are different, implying that L1 and L2 are intersecting or skew. Now suppose L1 and L2 are intersecting. We obtain the following system of equations. You have that 4 plus 2s equal to 2 plus t, negative 5 plus 4s equal to negative 1 plus 3t, and 1 plus 3s equal to 2t. Similar to the last example, what we're going to do is we're going to solve for s or t from the first equation, substitute into the second equation to find the remaining parameter, and then whatever you got for s and t, you substitute to the third equation or the last equations to find if you get the true statement or not. So here I observe that t is easy to solve in terms of s, so I get t is equal to 2 plus 2s, and I'm going to substitute t into the second equation, so substitute t into the equation negative 5 plus 4s equal to negative 1 plus 3t. We get that negative 5 plus 4s equal to negative 1 plus 3 times 2 plus 2s. And I'm going to find the value of s from here. I'm going to distribute 3 into the parentheses, and I get negative 5 plus 4s equal to negative 1 plus 6s. And if you solve the equations correctly, you should get s equal to negative 5. Now I get the value of s. I'm going to go back here and solve for the value of t. Then we get that t is equal to 2 plus 2 times negative 5, or negative 8. Next, we substitute s equal to negative 5 and t equal to negative 8 into the last equations in the system, which is 1 plus 3s equal to 2t. We obtain, so 1 plus 3 times negative 5 equal to 2 times negative 8. On the left-hand side, you get negative 14, and on the right-hand side, you get negative 16. So this is a false statement. Therefore, what this implies that L1 and L2 are skew. So that's it for me for this lecture. This is the first part of lecture 9. In this first part, look at the different forms of writing equations of a line, including parametric equations, symmetric equations, vector equations. We also learn how to determine if the two lines are parallel, not equal, if the two lines are equal, if the two lines intersect one another, and if so, can you find the intersection point, and if the two lines are skew. Alright, so that's it for me. Please let me know if you have any questions. Thank you.